Hello everyone, welcome. This is my IoT workshop. My name is Laura Żuchowska. I will be your lecturer today. Please feel free to ask questions like Mateusz said. And yeah, let's just jump into it. I will start with very simple introduction about me, mostly because dyvenia was already introduced by Mateusz. Then we will go through very fundamental theory about microcomputers. I will explain to you the very basics of IoT. Next, we will talk about the Raspberry Pi itself that we have on your desks, on all of them. We have 5 of them, 1, 2, 3, 4, 5. And finally, I will explain today's project, the sound detection. There will be a brief explanation on how to connect everything, the do's and don'ts of connecting, software examples and stuff. And finally, I would like all of you to participate in the hacking, so building and generally working around the software connected with IoT. I will help everyone after the presentation. If you have any questions, I will go desk by desk, one by one, to make sure that all of you understand everything. So don't hesitate. This is a safe space. You can ask any question. This is fine. I'm gonna make sure that all of the devices are set up properly, of course, and everything is connected. And yeah, without further ado, let's start. A short introduction was already made by Mateusz. We are a data consulting company. If you want to know more, we have also a newsletter if you would like to sign into. About me, maybe a bit. I've been working in dyvenia for about a year now. I am a team leader and I am a data engineer. I've graduated AGH University, majored in computer science. My hobbies are video games and art. Let's get into the theory, the topic itself, the IoT. We're gonna start with the basics, very basics. So what really is IoT? Internet of Things can be labeled as a group of sensors, inputs, outputs, everything connected together into one device, possibly using internet or any other form of communication, executing certain tasks. With the use of the software, everything can be measured, analyzed, calculated, noted down, whatever you need. The IoT also can be shortly described as a perfect example of hardware and software. Amazing solution. You can create really cool stuff with it. The output is really visible, it is trackable. You can work directly with the computer and understand exactly how it is executing and not just some abstract code going on somewhere, somehow. You can actually see and feel, literally feel the computer itself. IoT itself can vary. The projects can be incredibly complex, made by huge companies, by hundreds and hundreds of people working together on a simple, not simple, complex project. But they can also be very small, like LED light switching on and off button, for example. The sky is the limit here. There are no limits. One of the main parts of IoT is that it can collect and send the data to the database or any other data collecting component. Those measurements can be used later for further examination, analysis, graph creation, whatever it is that is required by this particular project. Moreover, IoT devices can reduce time and labor costs by automating tasks that would normally have to be executed manually by people. In order to connect to the cloud, you can send the messages by many different methods, such as messaging queues like MQTT, Message Queue Telemetry Transport Protocol. It's a very simple publish-subscribe method. Another one of those is Kafka, on which we actually held a workshop before. But not always you need to send messages and message queue to send data. You can simply even connect it via HTTP request and send this directly to the database. Huge part of IoT are microcontrollers. They are usually very small, can vary from just few millimeters long to ones as big as a post stamp. Every microcomputer, so what you have on your desks, is built with the usage of microcontrollers. Every microcontroller is responsible for a certain, usually one, task. A very important note, very important one, is that once microcontroller is already programmed, it is not possible for you to debug it. If it's running, it's running. For a programmer's perspective, it's like a black box. A bit. There is no feedback to you. Programming such a device requires the knowledge of assembly language. However, with the newer versions and, for example, Arduino, it also allows for the usage of C and C++, which you can then, when you write it on your PC, you can convert it into the machine code, so the assembly language. This method is called cross-compilation. Then you send it directly, this machine code, to the microcontroller, and once it's there, it's there. It's just doing its task. Microcomputers are bigger than microcontrollers. They can also be called SBC, so single board computers. One of the examples is what you have on our desk, is our lovely Raspberry Pi. But there is not only one version of it on the market, there are plethora of them. One of them is Arduino, which you may have seen, heard of. They usually specialize in microcontrollers, however, they also have an SBCs. But there are more of them, so for example, there is Vitalino, which is more specialized in anatomical and medical sensors. It is already built in such a way that it has a lot of inputs and outputs for tracking anatomical data. But generally, the specs of any SBC are much, much higher than those of the microcontrollers, even up to half gigabyte of built-in memory, for example, and an SD card slot available for you. Next topic, in the terms of the hardware, in IoT, are the sensors. There are a lot of different variables and types to buy, to look for, varying from stuff like air quality sensors, smoke detectors, pollution, gas, humidity, and so on. You could have anatomical and biological reactions like heart rate, galvanic skill response, much, much more. To conclude, it's almost everything that you need, and everything can be measured and noted down. As of this workshop, we will be detecting sound, and for this type event only, there are various sensors. One of them we will be using today. It's a 0-1 sensor for a sound for the microphone. It has adjustable sensitivity potentiometer, which I will talk about later. I would like you also to play around with that. In terms of wires, the standard ones for just very simple usage are the jumper cables. They have 3 types, so male to male, female to female, and male to female. The male ones are the ones with this metal end that you see on your desks. The female ones do not have the sharp edge, they have a socket. Now let's talk a bit about the software part of IoT. As far as the Raspberry Pi goes, you can use basically any language you want. By default, it already has a pre-installed C, C++, and a Python. But you can use JavaScript as well. It is fine. You just need to install it first with the configuration. For Arduino, however, only C and C++ are valid at the beginning. So if you are used to Python, it is easier for you to start up with the Raspberry Pi. It doesn't need any sort of setup from your side. We went through very basics of theory, so now let's jump into the Raspberry Pi itself. What is Raspberry Pi? The first single-board computer by Raspberry Pi was created in 2012. It was Model 1B, which was almost instantly followed by a cheaper version A. The main products of Raspberry are generally single-board computers, so Model 3A, which is the one that we have here. But there is also, for example, a Model 400, which maybe you heard of it. It's like a keyboard with a built-in computer. It's a very famous one. Another type of the product is the Raspberry Pi Zero. It's an ultra-compact version of a single-board computer. And the last but not least, Raspberry Pi Pico. It's a microcontroller. It's not a single-board computer, it's a microcontroller, which can be used for executing simple tasks, but could easily serve, for example, as a local web server for your house for very simple tasks that you need. Now let's have a look into the components of Raspberry Pi. As you can see in the image and on your desks, there is a main silver square in the middle, basically. This is the processor. On the left side, in the image, you can see there are 2 LED lights. One is for power and one is for signal. Power comes from the adapter, and signal is lighted up when there is any sort of signal coming from or into the Raspberry. Important note, if we have a power, so we connect our Raspberry Pi to the power adapter, that doesn't mean that the signal will be sent. So for example, our screen not necessarily have to show up because there is no signal, so the monitor will be off. Raspberry is powered up, but there is no signal, so the screen won't work. No, it is. Yeah. I don't believe so either. No, because this is very important for you to know if it's even working. Is it's like a debugging kind of thing for you. Um, okay, another one, another port that you see on the image is number 5, I believe, on the image. Yep, is the HDMI port. So to connect your screen. Port number 6 is the power adapter. So here you will have to connect your power adapters that are provided on the desks as well. Number 2 is for video and I believe audio, analog audio output. Number 4 is the USB. And number 7 are the pins that you can see. They are very sharp. Please be careful, by the way, when touching them. There are gloves here on the desks. And when you will be connecting everything, I would like all of you to use gloves. This is very important as to not damage any structure on the Raspberry or cables and any other device that you have. On the other side of the Raspberry, also, there is a input for SD card, which will be serving as your OS, basically. It is mandatory to have it, so don't pull it out, please. Don't take out the SD card. Mhm. Yeah?
Silver box in her left corner with a raspberry printed on it
Um,
without number.
yeah, it's without a number. Yeah, might be the memory. I believe so, yeah. Why is the SD card mandatory? And I would very much not like you to remove it because it contains your OS of the Raspberry itself. We already handled the setup, installation of the operating system, so please don't remove it. You don't have to worry about the installation or anything connected with that, so please don't change it, don't remove it, don't put your own SD card inside, please. This is very important. I will now talk briefly also about use cases of Raspberry Pi projects. When it comes to them, generally, it's a never-ending story. If you want, you can look up on Google Raspberry Pi projects and you will have tons of them. But I think I would like to tell you a bit about our real projects that we've built here in our private time. It's gonna be more, actually real, that you can build those. One of them is actually the one built by our Michał, who is sitting there. Yes, he's waving to you. The code is available on GitHub also, if anyone is interested in that. The project was aimed to track data about air quality inside his apartment. The data is tracked down, saved to database, and then displayed as visible here in the graphs and in the table. So every change, negative or positive, can be noted and tracked down by you. You don't have to buy the fancy air quality meters and stuff. You can just build it yourself, which is pretty cool, honestly. The next use case I will briefly explain is a part of my bachelor and master's thesis. I was conducting an experiment in which we had to track data from experiment. We had to track data from the subject's bodily changes while they were playing 3 different video games. And then we had to cluster the sensor data based on the emotions and the differences in the body that was visible for the subject. The article is also available online if anyone would be happy to read it. Of course, Raspberry Pi is not a solution to everything. There are many cases in which you absolutely don't need a computer with amazing specs to run your projects. So when to actually use Raspberry Pi? First case, very important one, is remote connection. Raspberry Pi by default allows for connecting wirelessly through Bluetooth, Wi-Fi, and any other methods, which the first 2 are basically already built in. So you just need to write some software to particularly use it. But generally they're already built in, you won't have to worry this much about them. The second use case is the complexity. Raspberry Pi is a very powerful computer for a single board computer, and it can run many complex tasks independently. And one last note, which is very important, fun. Not everyone likes working with C or C++ languages, so this is absolutely understandable. And this is where the Raspberry Pi comes in, with the Python as a default language. Additionally, there is a lot of sources on the internet, on projects, books, articles, and help that you can find on Raspberry Pi projects. I know that some people are really interested in the specs of the computers, so here is a list of what we will be working with today. The Model 3A Plus of Raspberry Pi. So for those of you who like to go into the insides of the computers, here is our list. What is the basic connecting workflow when we are working with the Raspberry Pi? Connect HDMI to your monitor, mouse and keyboard by USB. Remember, very important note, this model has only one USB input, so you have to use this dongle that should be laying around somewhere as well. This is for connecting both your mouse and the keyboard. It's for Bluetooth. It should be laying around somewhere. If it's not, then it's connected to your monitors.
Side of the monitor.
Yeah. Unless you are brave enough, you can just work with keyboards. That's also fine with me. If you are brave enough, feel free to do so. Generally, what you would also have to do when you first start up the Raspberry Pi is to put the SD card. Right now it is with the OS inside, but generally you would have to do it for the first time, set up everything, so set up your username, set up password, stuff like that. And of course, finally, plug in the adapter to the socket, the power adapter. In terms of GPIO pins, this is the schematics. For which pin does what. This is very important because if you connect them wrong, it will not work. GPIO stands for General Purpose Input Output. So you can see basically them whatever you wish. However you wish, you can do whatever. GPIO is for your sensors and other devices. Of course, voltage is for voltage, ground is also for ground, so you have a closed circuit. You will need to connect every sensor to a different one. You can't connect 5 sensors to one pin. It won't work. I'm not even exactly sure how you would do it, but if you manage to do so, it won't work. So yeah, but by the end, when you have everything connected, you will have a map of all the pins available. I will show up this slide at the end, so you will know which pin to connect to. Don't worry about it. This will not disappear suddenly.
Lights.
Yes, it will be available here as well. Oh, you mean after the workshop? Yes, probably we will send them through the meetup. How to connect via laptop? As you can see, you will not connect your laptops to the Raspberry Pi directly. Please connect to this Wi-Fi here that you see. The password is visible also. The RPIs will also have to have connection to this one. So you need to connect on your Raspberry Pi to this and your laptops as well to this Wi-Fi connection. Please check the names of the IP addresses and the names in the terminal when you are connected to the Raspberry Pi. And then you will use this command on the bottom, SSH, to connect from your laptop to the Raspberry Pi. So you will have a remote connection from your laptop to the Raspberry through the Wi-Fi connection. So it is by default on Windows and Linux. Yeah. You can work multiple laptops on the same Raspberry. It is fine. It is available. You don't have to worry about going one-to-one. Okay. We finished this section, so now let's jump into the final part of the presentation. I will explain the project, how to connect all the devices together. Let's have a program that will print the information about sound being detected by the microphone. Please, very important, also as I mentioned before, use the gloves. Do not touch microphone. This is this circle thing on the image, on the microphone. Do not touch it with your fingers. Do not poke at it, etc., etc. It's a very delicate device, so be careful. Additionally, this blue thing that you see in the image is the potentiometer. Here are also the screws. I would like you to play around with it. It will change the sensitivity of the microphone. If you would like to build an Alexa in the future, we need to start very slow. That's very important. Take your time and set the milestones. Your first milestone is building a simple sound detection system, not voice recognition. This is very important. Voice recognition is an extremely hard task. It is a very good, goal, but let's start simple. So we know the basics and the foundations. And this is basically exactly why this is our first milestone, to start slow. Um, yeah, and as I mentioned, this blue potentiometer, yes? Your own? Yes. It will require a lot of work, yes? Wait, you mean connect directly to Alexa with the Raspberry Pi and yeah, it could be possible, but you would have to first. It will not. Writing the voice recognition will not be as hard as changing the OS and the program that is already inside Alexa. You would have to somehow overwrite the Alexa itself. So this part, yeah, this is gonna be hard. I mean, if you're up to fight with Amazon, then sure, go for it. But on the image here, you can see how it should look like in the finished part. First, we need to set up everything, of course. So the power comes at the end, because once you start up with the power, it will start the system. It will already know what is plugged in and what is not plugged. So connect the microphone to the pins. Power, ground, and the voltage are written inside the microphone, on the microphone, so we will know which pin should connect to what, to which pin inside our Raspberry Pi. So don't worry about this. This is all written down on your microphone. You will have to connect your keyboards and mouse and HDMI for the screen, so you can see what is happening on the Raspberry Pi itself. Very important note, don't use too much force when setting everything up. Brute force is not the solution. Very important, please don't break it. And as I mentioned before, please use the gloves. What about the software? You will need to do basically 5 steps. First, you will need to import the GPIO module from the Python, from the already set up prepared Raspberry Pi library. So that's just that. You will need to set up the pins that you've used. So set the number of the pin that you had, that you connected to, and use this one. Create a callback method with the printing and attach it to your event detector. Put it in a loop, and that's all. You can enjoy. This is fine. The code should look something like this. I will remove this slide because I want you to work on your own, but you can have a look here. It shouldn't be one-to-one the same, honestly. Please play around with it. So try different pins. Try using a different method instead of a callback. There is a method here, as you can see, I used add event callback. Please use a different one, events detected. You will have to add the method from the GPIO library, add event detect, but please use a different one for the callback itself. For using actually printing the information, please use a different method here. Try reading both rising and the falling signal and the both version. See what are the differences. See what happens when you add into this code, for example. What would happen if you print the else statement from this input, from this particular pin? When does it print? Play around a lot with it. Play around with the potentiometer. So check which sounds are easier to detect, high or low frequency. How far do you need to have microphone from your mouth to actually detect it? Play around with it. Do whatever you want here. Just please do it safely, of course. Safety first. Gloves first, stuff like that, okay? And that's all from my side. So let's just go through it.